So today we're diving into what might be the most ambitious, most audacious quest in all of science, the search for a theory of everything. Now, this isn't just about finding some new particle. Nope, this is about finding the ultimate why, a single, elegant idea that explains everything in our universe, from the instant of the Big Bang right down to the way a single electron zips around. Let's jump right in. You've got to love this quote from the physicist John Archibald Wheeler. It so perfectly captures the heart of one of the two main characters in our story, Einstein's theory of general relativity. And it's more than just poetry, it's a deep, deep truth. See, in this view, gravity isn't some mysterious force pulling you down. It's the actual shape, the geometry of the universe. Think about a bowling ball on a trampoline. It creates a curve in the fabric, right? And if you roll a little marble nearby, it just follows that curve. That's it. That's planets orbiting stars. And this idea, this dynamic, flexible spacetime, is at the very center of the incredible conflict we're about to explore. All right, so here's our game plan. First, we're going to look at why physicists have been obsessed with finding one single theory for centuries. Then, we'll meet the two reigning champs of modern physics and see why they just can't get along. After that, we'll check out two of the wildest ideas proposed to solve this problem, face the massive challenge of actually testing these things, and finally, we'll look ahead to the future of this epic quest. You know, this search for a theory of everything isn't some new fad. It's pretty much the main engine that's been driving physics forward for hundreds of years. There's this deep-seated belief that underneath all the complexity we see, the universe is actually, at its core, stunningly simple and unified. And really, every huge breakthrough has been another step toward revealing that single underlying reality. And you can really see this relentless march toward unification throughout history. Back in 1687, Isaac Newton comes along and realizes the same force that makes an apple fall from a tree is what keeps the moon orbiting the Earth. Boom! Heavens and Earth unified. Then, in the 1800s, James Clerk Maxwell shows that electricity, magnetism, and even light are all just different faces of the same thing, electromagnetism. And then, much more recently, in 1968, we saw the electromagnetic and the weak nuclear force, two totally different seeming forces, merge into one. I mean, each one of these was a revolution, getting us closer and closer to that ultimate goal. The problem is, the next step is the hardest one yet. So today, our entire picture of the universe rests on two gigantic pillars. Each one is an absolute masterpiece, tested and proven to be right with just mind-boggling accuracy. And yet, they fundamentally disagree with each other. They paint two totally different pictures of reality. So let's meet these two titans, general relativity and the standard model of particle physics. And this slide really lays out the great divide. Over on one side, you've got general relativity. It's the majestic, sweeping story of the big stuff, planets, stars, galaxies. It describes a smooth, elegant, geometric reality. But then, on the other side, you have the standard model. This is the wild, chaotic world of the ultra-small. It's a jittery, uncertain reality governed by the laws of probability. They aren't just different rulebooks, they describe two completely different kinds of universes. And make no mistake, general relativity is astoundingly successful. It's the theory that let us understand the Big Bang itself. It predicted that starlight would literally bend as it passes by the sun, something that was proven true way back in 1919. It told us that things like black holes must exist, these monsters in space that not even light can escape. And then, in 2015, after 100 years, we finally heard the universe ringing like a bell from gravitational waves. It's just an incredible theory. Meanwhile, down in the quantum world, the standard model is the undisputed champ. It's like the ultimate periodic table for all the fundamental bits and pieces of reality. It brilliantly weaves together three of the four basic forces of nature. And its predictions, well, they're so precise, it's almost spooky. We're talking like predicting the distance from New York to LA and being off by less than the width of a human hair. The cherry on top, of course, was finding the Higgs boson in 2012, the particle that was the final missing piece of the puzzle. So we have two theories that work perfectly in their own domains, but what happens when those domains overlap? What happens at the very center of a black hole, or in the first yoctosecond of the Big Bang? That's where the world of the very large and the world of the very small become the same world. And it's right there, in those extreme places, that both of our beautiful theories just break. Their equations spit out nonsense. And this is the core of the problem, right? If they're both so ridiculously good at what they do, why can't we just use both? Well, because their disagreements aren't just minor details. They have completely fundamentally different views on the nature of reality itself, from the texture of space to the very meaning of time. Okay, this gets a little technical, but it's at the mathematical heart of the problem. In quantum physics, you often get equations that spit out the answer infinity, which is obviously not helpful. For the standard model, physicists have a really clever box of mathematical tools called renormalization that lets them tame those infinities and get real answers. But when they try to use those same tools on gravity, it's a disaster. It's like trying to put out a raging wildfire with a squirt gun. The infinities just explode everywhere, and the theory becomes completely useless. It's a total mathematical breakdown. And beyond just the math, there's a huge disagreement about what space even is. General relativity imagines space-time as this smooth, continuous fabric, like a perfectly calm lake. But if quantum mechanics is right, and you could zoom into the tiniest possible scales, that calm lake would actually be a raging, chaotic, boiling sea of energy, a quantum foam, where particles and even tiny universes are constantly popping in and out of existence. A smooth lake and a boiling sea. They just can't both be right. And this one might be the wildest of all. It's about time itself. In the quantum world of the standard model, time is like a universal clock, ticking away at the exact same rate for everything, everywhere. It's just the background. But in general relativity, time isn't a background. It's part of the show. It's a river that can speed up and slow down. Time literally flows slower for you if you're closer to a massive object. And this isn't just theory. Your GPS has to account for this every single second just to work. So which is it, a rigid clock or a flexible river? They can't both be the ultimate truth. So how on earth do you fix a problem this deep? You can't just patch it up. You need a complete revolution. You basically have to tear down everything we thought we knew and start over. And this has led to some of the most creative, most out there ideas in all of science. So now, let's meet the two main contenders trying to claim the throne. Here they are. On one side, you have string theory. Its big idea is that at the very bottom of it all, there aren't little point-like particles. There are tiny, vibrating strings of energy. And just like a violin string can play different notes, these strings can vibrate in different patterns to become every particle and every force we see. It's an incredibly ambitious idea that also happens to require extra hidden dimensions of space. Then you have loop quantum gravity. It takes a different approach. It says, forget the strings, what if space-time itself is made of tiny, indivisible chunks or atoms of space? In this picture, space isn't the stage where the universe happens. Space is one of the actors. Okay, so these are just two beautiful, mind-bending ideas. But they, and pretty much all the other contenders, share one gigantic, colossal problem. We have almost no way to test them. The amount of energy you'd need to actually see these strings or these loops of space is just so far beyond anything we can build. It leaves these incredible theories stuck in a kind of scientific limbo. Just look at that number. It's a quadrillion. The energy level where we think all this quantum gravity stuff happens, this so-called Planck scale, is a quadrillion times more powerful than our biggest machine on Earth, the Large Hadron Collider. To put that in perspective, if we wanted to build a particle accelerator powerful enough to reach those energies, it would have to be about the size of the Milky Way galaxy. That's the challenge we're up against. And this enormous energy gap has totally changed how physics is done. All those other big unifications in the past, they were guided by tons of clues from experiments. But today, it's a completely different game. Physics are sort of like explorers trying to map a continent on the other side of a massive, uncrossable desert. They don't have direct clues, so all they have to guide them is the compass of mathematics and the hope that the final answer will be beautiful and elegant. It's why things have gotten so speculative. So where does all this leave us? Well, we're in a really unique and, frankly, a very difficult moment in the history of science. We've got all these brilliant, revolutionary ideas floating around, but they're all just out of reach. We can't test them to see which one, if any, is right. The final chapter in this story just hasn't been written yet. This table gives us a great final look at the contenders. You've got string theory, which tries to unify everything, but it has this huge issue called the landscape problem. Basically, its equations don't predict one universe. They seem to allow for something like 10 to the power of 500 different possible universes, all with different laws, which, if anything is possible, does the theory really predict anything at all? Then there's loop quantum gravity, with its elegant idea of space atoms.
Its big hurdle is showing how our familiar, smooth reality emerges from those tiny, discrete pixels. It's a problem they call the classical limit. And there are other ideas too, like asymptotic safety, that are trying to find a path forward. Each one has its own strengths, but each one has its own massive mountain to climb. And that really brings us to the final and maybe the most important question. This whole quest is this amazing testament to human curiosity, to our belief that we can understand the world around us. But will we ever actually get there? Will we one day hold the final theory, the ultimate rulebook for the universe? Or is it possible that reality is just a story that never ends, with new layers of truth to uncover forever? We don't know the answer, but the search itself, well, that's one of the greatest adventures we've ever been on.